For more than 8 decades, the physical location of Lockheed P-38J Lightning, serial number 42103-993, remained unconfirmed in the field. The aircraft, famously known as the first of 3 P-38s to carry the Marge name and markings associated with Captain Richard I Bong, vanished during a weather reconnaissance flight. When an aircraft disappears into Papua New Guinea's dense tropical jungle, the terrain immediately begins to absorb the physical evidence. The primary constraint on resolving this specific wreck is not just the sheer density of the vegetation, but the legal and operational boundaries that typically apply when wartime debris is located on sovereign land in Papua New Guinea, including reporting and permitting expectations tied to national heritage oversight. The loss occurred on March 24, 1944. Although the aircraft was assigned to Captain Richard I Bong, it was being flown on that mission by Second Lieutenant Thomas E. Malone. The aircraft was flying out of Nadzab Airfield, tasked with probing atmospheric conditions ahead of future operational flights. Weather reconnaissance missions intentionally placed airframes into developing storm systems to gather critical meteorological data. When a severe mechanical cascade forced the pilot to abandon the aircraft, the unpiloted Lightning dropped into an uncontrolled descent and struck steep, jungle-covered terrain inland. That high-energy impact, combined with decades of erosion on a slope, dictates the reality of the wreck site today. Following the crash, search efforts at the time were severely limited by poor visibility and the unforgiving terrain. The impact zone went cold, an unmarked point swallowed by the jungle. Seasonal monsoon rains and aggressive jungle growth layered over the shattered aluminum skin, completely isolating the P-38 from the outside world. In 2024, Pacific Rex and the Richard I Bong Veterans Historical Center mounted a joint expedition into this valley with a single procedural aim: locate and definitively authenticate the impact site of the 42103-993 airframe. This was never framed as salvage. Working under Papua New Guinea heritage oversight and a non-invasive protocol, the team could only document what was visible and leave every major piece exactly where it lay. On the ground, the limit was absolute. The team had to prove identity without shifting heavy structural debris, without excavating the buried engines, and without breaking the wreckage matrix. They entered the jungle with survey discipline, not recovery hardware. Their mandate was simple: verify, record, and leave it in place, exactly as gravity and the jungle had arranged it. That leave-it-in-place mandate creates a hard bottleneck for forensic verification. In a standard recovery, investigators would go straight to metallic data plates on engine blocks or structural bulkheads to lock down an airframe serial number. Here, that shortcut was off the table. The team had to build proof from what the surface still exposed, or what could be revealed with a careful handbrush of loose topsoil. The survey team had to read the surface scatter perfectly. A high-speed ballistic impact drives a mass downward. The engines and other heavy assemblies behave like kinetic penetrators, burying themselves at the base of the ravine. Lighter structures, wings, tail booms, cockpit framing, shatter and fan out across the steep hillside. Every step through that topography carried the same frustration. The most definitive proof was likely still sealed under feet of soil. Finding wreckage in the jungle is only half a win if you cannot prove which airframe it is. Without a confirmed serial number, aluminum on a slope is just anonymous debris. Pacific Rex mapped the visible footprint, reconstructed the crash sequence, and hunted for an exposed factory mark. Then photographed and geologged each step into a chain of custody built on images, not possession. How does a survey team map a high-energy impact zone and prove the identity of a specific aircraft when the primary mass is permanently buried under jungle topsoil? At 30,000 feet, a mechanical anomaly forced a critical trade-off between troubleshooting a failing engine and escaping a deteriorating weather system. The flight profile placed the aircraft inside a severe weather front characterized by heavy, overcast, and turbulent air. Exactly 50 minutes into the mission, the left engine cooler shutters malfunctioned. Not long after, the radio failed as well, isolating the aircraft from ground control and stripping the pilot of any external situational awareness. Operating a twin-engine fighter in zero visibility requires instrument reliability and stable power. When the left engine failed shortly after the radio loss, the emergency compounded into an irreversible cascade. Electrical problems were reported as the situation worsened, further degrading cockpit systems and controllability. This sequence of failures stripped the pilot of practical options to manage the dead engine and maintain safe flight. When a power plant fails on a multi-engine aircraft, the immediate operational constraint is drag. The pilot must feather the propeller, rotating the blades toward a low drag angle aligned with the relative wind. If feathering cannot be accomplished, the failed side can be left with a windmilling propeller that generates heavy drag. That windmilling drag can act like a powerful aerodynamic brake on the dead engine side. This mechanical lock created a catastrophic geometric imbalance. The right engine was still producing forward thrust, while the left side of the aircraft was anchored by the massive drag of the windmilling disc. This imbalance induces an asymmetric spin drag. The opposing forces create a lever effect, violently twisting the nose of the aircraft toward the dead engine. In standard flight, a pilot uses the rudder to counteract this yaw. In this scenario, the drag was so severe that it easily overpowered the maximum aerodynamic authority of the rudder. The aircraft yawed uncontrollably to the left, stalling the wing and forcing the airframe into a violent, disorienting spin. Inside the cockpit, the pilot faced a terminal decision logic. Aerodynamic recovery from a fully developed asymmetric spin requires restoring balanced thrust or drastically reducing drag on the dead side. The total electrical failure guaranteed that neither option was physically possible. He could not feather the left propeller, and he could not restart the engine. Attempting to wrestle the spinning airframe through severe weather with zero visibility and no instrumentation was an unrecoverable dead end. Strict adherence to survival protocol dictated only one viable choice. He had to abandon the aircraft. The pilot successfully bailed out of the spinning fighter at about 11,000 feet, according to the mission account. This altitude established the baseline for the final phase of the flight. The moment the pilot cleared the cockpit, the P-38 transitioned from a controlled mechanical asset into an unpiloted ballistic mass. Without control inputs, the heavy twin-engine fighter accelerated into a steep dive. The aerodynamic forces generated by the asymmetric drag locked the airframe into a high-speed, nose-down trajectory. The aircraft plunged through the heavy overcast, dropping rapidly through 11,000 feet of empty airspace. The sheer mass of the engines and the concentrated weight of the forward fuselage dictated the angle of attack as it plummeted toward the earth. The flight ended when the nose of the aircraft violently impacted the dense tropical canopy of Madang province. Once the airframe shattered against the ravine, the debris field was surrendered to rain, roots, and slope erosion. Even modern aerial reconnaissance still depends on what the canopy will let you see. In rugged jungle terrain, cover and shadow can hide small metal or soil-buried wreckage, turning imagery into an educated guess. That sensor ceiling forces the same conclusion pilots faced in 1944. Sooner or later, verification has to happen on the ground. To locate a specific target like a World War II fighter, search teams must transition from airborne technology to physical ground movement. By 2024, Pacific Rex and the Richard the Fur Bong Veterans Historical Center were in the field to pin the missing P-38 to an exact defensible location. Walking blindly into the mountains of Papua New Guinea guarantees failure. The jungle is too vast, the terrain is too steep, and the physical hazards require a strictly defined search perimeter before boots ever touch the ground. The solution requires an archival search grid. Before navigating the physical environment, investigators must synthesize disparate historical records to draw a bounded probability polygon. They pull 1944 weather report, squadron combat loss logs, and the exact coordinates where the pilot was rescued. By plotting the pilot bailout point and factoring the estimated drift of an unpiloted airframe falling through severe weather, the team mathematically narrows the geographical footprint. They cross-reference this calculated drop zone with historical maps of local plantation boundaries from the era. The math gives you a place to start, nothing more. Archival targeting only works when you treat every wartime coordinate as suspect. In 1944, positions were often estimated under duress, logged in turbulence, and recorded without satellite reference. Trust one document blindly and you search the wrong valley. By layering the radio failure timeline over the moving weather front and the verified rescue location, the expedition isolated the overlap worth walking. Once the archival grid is established, the physical execution begins. Ground teams must traverse the steep terrain on foot, They operate under a severe visual limitation. Line of sight on the jungle floor is frequently restricted to less than 50 feet. Investigators must walk systematic grid lines, manually checking heavy underbrush and steep inclines. They search for unnatural geometry, sharp aluminum edges, or synthetic color variations that break the organic pattern of the vegetation. The physical traverse demands strict operational discipline. Ground teams must maintain their heading through dense vegetation, ensuring they do not drift off their assigned grid lines. When a search grid intersects a sheer drop or a tangled thicket, the team must navigate straight through or carefully log a detour. Deviating from the mathematical grid without tracking the offset creates gaps in the search coverage. Missing a single swath of terrain means walking right past an airframe hidden beneath decades of accumulated topsoil and biomatter. The rigorous application of this synthesized data yielded concrete results. In mid-May 2024, with reports placing the intercept on May 15th to May 16th, the joint expedition successfully intercepted the target inside the predicted search box. The archival grid reconstruction method worked exactly as designed. The team successfully transitioned from 80-year-old paperwork directly to the physical wreckage. The transition from a theoretical map to a verifiable physical location marks the strict boundary between search operations and forensic documentation. The joint team proved that when the canopy keeps sensors guessing, disciplined historical synthesis still hits the mark. Drawing a search box on a map is only the first step. Navigating the actual topography requires interpreting how gravity alters a crash site over 8 decades. The physical footprint of a high-speed aircraft crash in mountainous jungle defies standard geometric expectations. The wreckage of this specific airframe does not exist in a concentrated, easily measurable circle. Instead, the debris field stretches downslope in an elongated pattern across a broad patch of jungle terrain. This massive, elongated scatter pattern is not solely the result of the 1944 impact sequence. It is a direct product of the steep ravine topography and 80 years of continuous environmental degradation. For an investigative team operating under strict, non-invasive rules, the sheer scale of the site presents an immediate geographical constraint. When an aircraft shatters on a steep incline, the resulting fragments do not remain static. The dense canopy overhead traps moisture, creating a permanently saturated environment on the jungle floor. Over decades, where seasonal rainfall and constant soil subsidence force a relentless gravity debris shift. Lighter, unanchored aluminum structures, such as torn wing sections, tail booms, and shattered cockpit fairings, slowly slide downhill away from the initial strike zone. This continuous, erosion-driven migration disconnects the surface scatter pattern from the true kinetic point of impact. The investigators are forced to navigate this elongated debris field, recognizing that the visible metal on the lower slopes is merely the runoff from the primary crash site. To understand the actual geometry of the loss, the survey team had to read the terrain in reverse. They tracked the migrating aluminum uphill, moving against the flow of erosion. Every piece of torn metal had to be mapped and photographed exactly where it lay, documenting its drift without altering its position. This methodical tracking process was necessary to locate the absolute center of the impact. The trail of fragmented aluminum eventually narrowed, leading the ground team to the base of the steep ravine where the actual high-energy strike occurred. At the epicenter, the limit was literal. Both Allison engines had punched deep into saturated soil, leaving only fragments of associated hardware visible above the mud. This geological encapsulation creates a severe forensic boundary for the investigators. In most historical recoveries, investigators go straight for the engine block because crankcase plates can settle an identity quickly if you can reach them. Here, access was the problem, not the theory. The engines of this P-38 survived the crash, and their burial may have shielded some surfaces from direct exposure. But wet, acidic soil and root activity can also accelerate corrosion, so any data plates may be intact, degraded, or obscured beneath the earth where the engines came to rest. However, knowing the data plates are present is entirely different from being able to read them. The engines are locked beneath feet of dense, root-bound earth. The strict operational limits governing the expedition explicitly forbid the team from using shovels, winches, or heavy equipment to excavate the mass. The heavy engines cannot be accessed and the structural matrix cannot be severed. The team was forced into a physical standoff with the terrain, staring at the exposed propeller tips of a deeply buried puzzle. With the primary engine data plates hopelessly buried beneath dense earth, the team had to find an alternate forensic method to confirm the identity. A P-38 lay shattered in the ravine. But the case stayed open until a number could be proven. Establishing that identity without breaching sovereign wreckage laws requires relying entirely on fragile surface anomalies rather than deep excavation. The expedition team faced a strict procedural boundary. They could see the scattered aluminum, but turning that debris into a verified historical record required absolute evidence discipline. Everything was logged in place: photos, measurements, and coordinates, because nothing could be cut, pried free, or removed. Because gravity debris shifts scattered the lighter structural components across the steep slope, the investigators had to meticulously examine the outer wing panels and tail sections that remained above the mud. They knew exactly what visual anomalies to look for. This aircraft was the first of 3 P-38s eventually named Marge. However, verifying the specific airframe presented a unique visual challenge. Unlike standard military aircraft of the era, this specific fighter did not feature painted nose art. Instead, an enlarged photograph of Marjorie Vattendahl was originally adhered directly to the bare aluminum nose. 80 years of heavy jungle rain, humidity, and biological growth destroys organic material and photographic paper almost immediately. The investigators knew that searching for the famous nose art was a physical impossibility. The team had to look for durable chemical signatures that could survive decades of tropical exposure. Specifically, they targeted the distinctive red paint originally applied to the wing tips, tail tips, and propeller spinners of this exact aircraft. By carefully brushing away decades of accumulated biomatter and leaf litter by hand, the investigators located surviving patches of this exact red paint on the scattered wingtip and spinner fragments. Finding these specific color markers provided a massive circumstantial indicator that they were standing on the correct airframe. However, circumstantial evidence does not satisfy the strict burden of historical proof. Another aircraft from the same fighter group could potentially feature similar squadron colors. The expedition required absolute numerical verification to close the case. To achieve this without accessing the buried engine blocks, the team had to locate factory serial paint. This refers to the military factory applied paint block numbers used to identify specific airframes when physical metallic data plates are detached, corroded, or inaccessible to non-invasive survey teams. During manufacturing, the last few digits of the aircraft serial number were routinely stenciled onto major external components, including the vertical stabilizers and the outer wing panels. The investigators focused their manual clearing efforts on a largely intact section of the right wing structure resting on the slope. They executed a highly controlled surface clearing process. With bare hands and soft brushes, they eased back wet topsoil and moss, careful not to score the aluminum beneath. As the bare metal emerged, a distinct United States Army Air Force stencil became visible against the oxidized surface. The black factory paint had survived beneath the protective layer of dirt. The team immediately photographed the finding, securing the visual data into the chain of custody. The stencil appeared to show the numbers 993, consistent with the final 3 digits of the missing aircraft serial number, and it was documented in photographs as part of the expedition record. Taken together, the surviving red paint on key extremities and the documented 993 marking gave the team a high-confidence identification of the first Marge airframe. They accomplished their primary objective without a shovel, a lift, or a cut, only patient surface documentation. And that leaves one question. What does an expedition leave behind when the mission objective demands that nothing is taken? Leaving a positively identified aircraft untouched in a remote jungle is not a logistical failure. It is a deliberate legal trade-off. The wreck stays secure and the historical question still gets answered. Once the factory stencil on the wing was authenticated, the search phase was over, and the mission became strict data management. The historical weight of this specific airframe creates a unique vulnerability. Captain Richard Bong eventually secured 40 confirmed aerial victories during his combat career, making any equipment associated with his operational history highly significant. Because this Lightning was the first to carry the famous Marge designation, locating it was a primary institutional objective for the Richard I Bong Veterans Historical Center. In standard historical recoveries, finding a famous airframe often triggers an immediate, heavy engineering campaign to extract the metal for museum conservation and public display. In this case, that specific outcome was explicitly forbidden by international agreements and physical reality. Adhering strictly to the zero disturbance rule meant the survey team had to completely separate the concept of physical possession from the concept of historical proof. They had to operate under the absolute constraint that the physical aluminum, the deeply buried engines, and the shattered cockpit structure remain the absolute sovereign property of Papua New Guinea. The expedition could only claim ownership of the forensic data they painstakingly generated on the steep slope. By refusing to sever the structural matrix or excavate the impact crater, the team preserved the exact kinetic context of the 1944 crash. The site remains a pristine, untouched archaeological record of a high-speed ballistic loss. This extreme physical discipline directly enabled the final procedural phase of the operation. The transition from a lost wreck to a legally protected historical site requires formal institutional alignment. The investigators did not simply publish their findings and leave the remote location exposed to the public. Instead, they compiled a comprehensive forensic dossier. This technical package included the precise geographic coordinates of the impact crater, the topographical mapping of the elongated debris field, the photographic chain of custody verifying the factory paint, and a complete structural condition report of the exposed flight surfaces. This critical wreckage data was secured and compiled into a dossier intended for relevant stakeholders, including Papua New Guinea heritage authorities and the Bong Veterans Historical Center. That documented record is the measurable product of the 2024 expedition. It ensures that the host nation retains absolute control and visibility over its sovereign territory, while the Historical Center in the United States gains the verified operational closure it required. Securing the data also addresses a critical secondary hazard inherent to aviation archaeology. High-profile military wrecks become magnets for unauthorized salvage, souvenir hunting, and illegal scrapping once a location starts to circulate. To push back, the project prioritized coordination with local landholders and authorities who can physically watch the area. After the expedition, that relationship was reinforced through a sister city partnership between Poplar and Madang, signed in July 2025, creating a durable channel for local stewardship. Ultimately, protection depends on Papua New Guinea heritage enforcement on the ground. When a site is protected under these agreements, its scientific value stays locked in place. Because the 2024 team did not dig or drag pieces across the slope, the orientation of every shattered panel still points back to the dynamics of the 1944 impact. By synthesizing archival flight data and relying on surface-level visual authentication, the joint team closed the case without destroying the terrain. The first Marge airframe remains anchored in that steep tropical ravine, no longer an undocumented loss, but a verified, legally protected monument to the uncompromising realities of military aviation.